Okay, we're going to derive the third of the big three equations for motion in one direction under a uniform acceleration. So to begin with, what we're going to do is take a look at what our big three equations are. The first one comes from the definition of acceleration. Our initial velocity, or our final velocity, is VO plus AT. Our second equation is our equation for displacement, how far something will go in a certain amount of time. And that's x equals xo plus VOT plus 1/2 AT squared. Okay. Sometimes we're given a problem where we don't have time for initial conditions, including velocity and possibly how far something's gone. So that's what we want to find is where that equation comes from. V squared equals VO squared plus 2a delta x. So we're going to start with our first of the big three equations and solve for t. The reason we're going to do this is we have two equations that we do understand where they came from, and we have two unknowns. We have time, and then we have the other thing that we're looking for for a given acceleration. So what we're going to do is solve for t and substitute it into our equation for displacement. Okay, so the time equals change in velocity, v minus VO, over acceleration. We're going to substitute that in for time in our displacement equation. X equals xo plus VOT plus 1/2 AT squared. Okay, it's going to go into each of those places where there's a time, and you're going to see what that looks like. So wherever we see a t, we're going to put in v minus VO over a. So the equation looks like xo plus VOT. Let's finish this up here. The equation x equals xo plus VOT. Instead of t, we're going to have v minus VO over a plus 1/2 a. And then instead of t, we see v minus VO over a squared. That's where the t squared is. Okay, so now we have to do a little bit of algebra. We have to multiply all these terms out to get one really complicated equation. So here's what that looks like. So again, x equals xo plus VO v over a minus VO squared over a plus 1/2 a. And now I'm going to multiply this term out, this v minus VO squared. And that's going to look like v squared minus 2v VO plus VO squared. And that's why you learned how to do that in algebra, so you can do it here in physics. And then that's divided by a squared. Okay, so now we're gonna separate this out one more time and see what it looks like. So x equals xo, again, plus VOV over a minus VO squared over a plus 1/2 a. Now here we have to take a look. One of the accelerations on the top and the bottom cancel out. So we have v squared over 2a minus 2v VO over 2a plus VO squared over 2a. Okay, and what we're going to see here is that this term, VO over a, is the same as VO over a over here. One's positive, one's negative. So they're going to cancel out. And if you look at the denominators, they're not all the same. So we need to make them all the same so that we can combine these terms. So we're going to multiply by 2 at the VO squared over a. So now it looks like this. X, and I'm also going to subtract the initial x position over. So it looks like x minus xo, which is our displacement, equals 2VO squared plus v squared plus VO squared. And that's over 2a. And I missed a minus sign there. That's negative 2VO squared, the first term. So if I have VO squared minus 2VO squared, that's actually negative VO squared. So we're going to combine those two, and it's going to look like this. Delta x, multiply both sides by 2a, equals v squared minus VO squared. Okay. So solving for v squared, which is what we're looking for, v squared equals VO squared plus 2a delta x. And that's the final equation.